this is an extension of work which I presented at the meeting in San Antonio a year ago, as I've stated there. And this is how I have structured the talk. I've kept an eye on the literature there has been since the San Antonio talk on EROEI. And in particular, I've selected one recently published paper with ideas on EROEI, and I've compared its contents with the ideas expressed in the San Antonio paper. Now, the null hypothesis from which I shall work in comparing my San Antonio work with the independent work is that neither is better than the other. That is my, as I said a moment ago, where I'm coming from, the null hypothesis, as I critique the independent work and compare it with my own. Also, a blog appeared in which some of the views I'd expressed in the San Antonio paper were evaluated, and we'll take a look at those as well. Yes, we'll take a look at those as well. Now, amongst the recent utterances on EROEI, energy return on energy invested, is is accessible on this URL, which is a document of the Royal Society of Chemistry, the approximate counterpart in the UK of the American Chemical Society here. And there are statements on that which I'm going to take and critique. And the first statement is that at a rough comparison, conventional crude oil has an EROEI in the range 10 to 20, while tight oil comes in at 4 to 5, oil recovered from deep water drilling 4 to 7, heavy oil 3 to 5. And I'm going to look at those data in detail over the next few slides. Now, in the San Antonio paper, as well as in numerous other publications by now, one sees this correlation that the EROEI is 5.5 times 10 to the 5th divided by 25H, where H is the depth of the oil. So if it's an offshore well, then H is the well depth plus the sea depth. And that 10 to 20, given by the Royal Society of Chemistry for conventional crude oil, whatever that means, corresponds to well depths in the range 1,100 to 2,200 meters, all pretty standard. So thus far, we've established compatibility between that and the independent work described by the Royal Society of Chemistry. Now, the statement that tight oil comes in at 4 to 5, we now have to think about. Tight means, as I was saying in a comment only a few minutes ago, it means that it comes from a rock formation having low permeability. And the statement that tight oil comes in at 4 to 5 has no reference to the well depth, which is, of course, the major determining factor in the EROEI. So I then wondered whether the reason that a value somewhat below that for conventional had been assigned to tight oil was that the hydraulic fracturing process has an energy requirement which mortgages the oil field. In other words, once production has begun, a certain quantity has to be produced before the energy required for the fracking has been repaid. I wondered whether that was the origin of this 4 to 5. And I'm delighted that we have Dr. Ford in the audience, and no doubt he can add to the discussion of fracking which follows. Now, this is the sequence of events in hydraulic fracture. The geological formation is fractured open, usually with an aqueous fluid, sometimes anorganic fluid. The scene of the fracture is occupied by a proppant, and that's something else that was mentioned this morning when we were hearing about lignocellulosic materials. Oil exits the formation and experiences the permeability of the proppant in situ, rather than that of the rock formation. So there then is a summary of the processes involved in fracking. That's a jack-up rig recently used in fracking in the North Sea. Semi-submersible vessels are often used. We call fracking using a rig like that, rig-based fracking, or from a semi-submersible vessel-based fracking or fracturing. Well, there is a picture of a hydraulic fracturing truck for onshore fields. So we've seen the plant that's required for fracking, examples of the plant that's required for fracking onshore or offshore. And the power requirements of these devices have to be considered if we are to address the question of whether hydraulic fracturing significantly mortgages a field by way, or a well, by way of its own energy requirements. Now, I've taken a statement from a recent case study. In general, the process of hydraulic fracturing consists of injecting water, sand, and chemical additives into the well over a short period of time, typically less than 1 hour. I'll return to that point, but typically less than 1 hour, at pressure sufficient to fracture the rocks and enhance fluid movement through the perforations and into the well bore. Now, a mobile hydraulic fracturing unit, such as the one of which I just showed you a colour slide, will deliver at about 2,000 horsepower, or about 1,500 kilowatts. And it's a very basic calculation to show that if that's working at 30% efficiency, converting the heat in the fuel to mechanical work at 30% efficiency, the heat has to be supplied at 5 megawatts, and in an hour's operation, the quantity of heat will be 18 gigajoules. Now, it's a useful rule of thumb that a barrel of oil releases about 6 gigajoules on burning. So 3 barrels of oil, which is nothing, would be required to pay back the energy required to do the fracking. The well would have repaid its energy debt due to the fracking as soon as it had produced 3 barrels, which of course is utterly negligible. Even where fracking is in stages and occupying much longer time periods than an hour, still the payback requirement of the well to allow for the fracking is quite negligible. So it's difficult to know the basis of this 4 to 5 for tight oil, and of course I hope that some of you will have views on that I can take away. Now, the other statement in the Royal Society of Chemistry document says that oil recovered from ultra-deep water drilling gives an EROEI of 4 to 7. It has been shown in a short article in an Elsevier publication from a few years ago that the drilling of a well mortgages a well to a totally negligible degree. Oh, I've referenced it there. Now, what is ultra-deep water drilling? An example of a deep water field is the Thunder Horse field in the Gulf of Mexico. It's in the Mississippi Canyon, which is where the Macondo well is, where the very grave accident occurred 4 years ago. And at Thunder Horse, we were told of a well which was 6,300 feet below the sea. No, the well was at a sea depth of 6,300 feet, and the subsea depth of the well was 22,760 feet. So returning to the equation here, it's clear that the sea depth, the well depth contributes much more to H than does the sea depth. The well depth contributes much more to H than does the sea depth. And so it's difficult to understand why there should be this statement that in deep water the EROEI is jeopardized because of the depth. Heavy oil has an EROEI of 3 to 5. I think probably dense crude is a better term than heavy oil, but whatever. That's the range of API gravity, of density of crude oils, and it's not sufficient for there to be a factor of almost 2 in the EROEI between the lightest and the heaviest, the least dense and the most dense of the oils at the ends of that range. So again, we are not able to follow, or we're not able to fit the information given by that Royal Society of Chemistry document into the framework of EROEI, which I presented to you last year. Now, other developments since last year's paper has been this one. In Chemistry in Australia, I have written a critique of that for publication. It's been published, and there was no response. So we'll see what people here think in any way of the work by Morgan, which draws extensively on a paper by Hall in Scientific American. So I'm taking statements from Hall and from Morgan, and in an attempt to correlate them with what I presented last year, to put them in tabular form and make comparisons. Now, there's a difficulty with the very term EROEI. EROEI is clear. Energy return on energy invested. It's clear. It's one energy divided by another. And yet, so often, financial figures slip into it, even when it's so defined. But so defined, it is one energy divided by another. Now, the alternative term, EROI, stands for energy return on investment, and that can mean invested money or invested energy. So there needs to be clarification when the term EROI is used. Now, in the paper by Morgan, there's consistent use of EROI in the sense of EROEI, and the same is true of Hall, but at the same time, quite clearly in Hall's paper, there is confusion between barrels and dollars slipping in. Some EROI, just guessing at 6 to 1 to 5 to 1, it doesn't work anymore, and it's talking money, it's talking finance, and EROIs, which are not clearly in one paradigm or the other, energy or finance, can be difficult to interpret. Last year, I used the term adventitious energy, meaning energy, yes? Well, just a minute, we've got... Oh, okay. energy for which there's no alternative use in engineering practice. And that, I think, has sometimes been taken to signify interchangeability of energy and cost in formulating an EROEI. Yes, this statement here, if you've got an EROEI of 1.1, you can pump the oil out of the ground and look at it. If you've got 1.2, you can refine it. That disregards the fact that low-value natural gas used in a refinery need not be accounted for in the energy invested. It will be accounted for in any thermodynamic analysis, but not in an EROEI, because it's what is termed adventitious energy that there's no other use for in engineering practice. The fate of that natural gas otherwise would have been re-injection into the well or flaring. So the Morgan Hall paper says EROEI is a fundamental thermodynamic metric. It isn't. And over the few years since the term adventitious energy was introduced in relation to EROEI, there hasn't been much, I can't find much on the internet by way of use of the term, although it does seem to have slipped in to the Wikipedia entry for EROEI under different under a different name. Non-man-made energy, which is not usually included in the calculation of energy invested. That is in the Wikipedia entry for EROEI, indicating that the ideas on adventitious energy are starting to seep through to day-to-day reports and comments on EROEI. A rather startling statement in the work I'm considering is that ethanol is a crummy fuel. But it's an extremely good fuel. It has a research octane number of 108, as well as being carbon neutral, provided it's made from fermentation. So that's also surprising that it's been so described. Right, now the blog I mentioned, it says that the author of the blog accepts my point that EROEI is not an energy balance and said it's an entropy balance. That is very difficult to follow. I don't think a case for that can be supported at all. And, well, the rest of this will be in the printed form of the paper. So, thank you.